Hello, this is FlippedHarber for Precalculus. In this video we're going to talk about the complex plane. Our objectives for this lesson are to convert a complex number from rectangular form to polar form, to plot points in the complex plane, and to find products and quotients of complex numbers in polar form. The outline for this lesson will start by taking a look at what the complex plane is, then we'll find the magnitude of a complex number, also known as the modulus. We'll take a look at the polar form of a complex number, and then we'll take a look at converting a complex number to polar form into rectangular form. And then we'll end by taking a look at a theorem that deals with the products and quotients of complex numbers in polar form. So the complex plane looks a lot like the Cartesian plane, the xy plane, except our x-axis is labeled the real axis. It's the real component of complex numbers. The y-axis is now labeled the imaginary axis, so it's representing the imaginary component of our complex number. So if I want to plot a complex point, that is x plus yi, I just move over x on the real axis and then I move up y on the imaginary axis, and that would be our point z. Now this point actually happens to be 3 plus 2i. We'll do something with that in a second. Now our magnitude of this complex point is the distance. It's a real number. It's a distance from the origin to the point. Now finding distances on the Cartesian coordinate system isn't that big of a deal. If I asked you the distance from the origin to a point x comma y, you should be able to do that pretty easily. So finding this distance, the magnitude of the complex number, should not be very difficult. It's actually an application of Pythagorean's theorem. So the magnitude of the imaginary number, denoted here with these double bars, looks like an absolute value. It's not. It means magnitude. Is just equal to the square root of x squared plus y squared. That is the real coefficient squared plus the imaginary coefficient squared. So pretty basic stuff that you should all be very used to. Now let's go ahead and find the magnitude of this point if it actually is 3 plus 2i, and that's actually what I plotted, so that's what it is. So the magnitude of this this complex number is the square root of 3 squared plus 2 squared, which is equal to the square root of 13. Again, should feel pretty familiar. Another way to find the magnitude of a complex number is actually to take the square root of the complex number times its conjugate. So here we see the conjugate of z. This little bar means conjugate. And if you remember, the conjugate means that we change the sign on the imaginary portion only. So z is x plus yi. The conjugate of z is x minus yi. So the magnitude is equal to the square root of that product. Okay, now let's talk about polar form for a complex number. It's going to look very familiar. We're taking an x and we're changing it into r's and theta. We're taking a y and we're changing it to r and theta, just like we did before. We're going to do just a tiny bit of algebra extra. It's not going to be anything difficult at all. So I want to take the complex number z equals x plus yi, and I want to convert it to polar form. So I'm going to make the exact same substitution I did in previous lessons, where I replaced x with r cosine theta. Y I replaced with r sine theta. Now that little bit of tiny algebra extra, we're just going to factor out that r. So this right here is our complex number in polar form. We've got the r out front, we've got cosine theta plus I sine theta. It's just more standard to move that I out in front. Now let's take a look at what this looks like on our complex plane. So we're kind of putting the polar system on top of our complex system, and we see that r is, again, the distance from the origin. That's nothing unusual. That's what r meant before, but now r is really just the magnitude of this complex point. So this is actually equal to the square root of x squared plus y squared. Our theta, just like it was before, is an angle measured from the real axis or from the polar axis. Kind of one and the same here. So this is what a complex number in polar form looks like. Okay, so let's go ahead and convert a complex number to polar form. So here we have it in x plus yi form. Now, how do I know it's in rectangular form right now? Well, there's an extreme lack of cosines and sines. So I know it's in rectangular form. So my first task would be to find r. Well, it's equal to the square root of x squared plus y squared. Remember, the square root of 3 squared is just 3. Now this is 12, so pull the 4 out, it becomes a 2 times the square root of 3. And the theta, there's different ways to find it. You should be used to finding theta using a tangent inverse, so that's what I went ahead and did here. I used the tangent inverse of y over x. So this is equal to pi over 6. Just look that up on your trig table. So putting it all together, z is equal to r, 2 square root of 3, times cosine theta, that's pi over 6, plus I sine theta, which again is pi over 6. Now yes, we could look this up on our trig table. We can look up sine of pi over 6 very easily. We can look up the cosine of pi over 6 very easily. That's not the point though. Don't do that. Leave the cosine, leave the sine, because they're telling us the angle in polar form. So leave the cosine and sine. Don't look up what they are equal to. Okay, so let's go the other way. What if we have 2 cosine of pi over 6 plus I sine of pi over 6? Well, the first thing I'm going to do is multiply that 2 in. So I've got 2 cosine pi over 6. So this is r cosine theta. This is my x value. 2 sine of pi over 6. This is my y value. So I go ahead and look up what the cosine and sine are. Square root of 3 over 2 and 1/2. Go ahead and simplify. The 2's cancel in both spots, so z is equal to the square root of 3 plus I. Now, why are we do this? Well, it turns out that it's easier to do some math, namely products of complex numbers and quotients of complex numbers, when they're in polar form. So here we have a theorem that tells us how to find the product and the quotient of complex numbers when they are in polar form. And especially this one right here is a lot easier than doing it in rectangular form. If you think way back, you might remember dividing complex numbers. This is actually much, much easier. Maybe this isn't necessarily easier, but we're going to look at some things in the next video that are definitely easier in polar form instead of rectangular form. So here we see the product of 2 complex numbers, z1 and z2. It's equal to the product of the radii. And our cosine and sine are still here, and they're acting on the sum of the 2 angles. If we want to take the quotient of 2 imaginary numbers, z1 and z2, we take the quotient of the radii, and we subtract the angles. Now notice it's the theta 1 minus theta 2. 1 is on top, 2 is on bottom. So make sure you don't mess up that order. And then the sine is operating on the exact same thing. Now I'm not going to use any trig identities or anything on this. I'm literally just going to subtract the angles. So let's go ahead and take a look at an example. We have 2 complex numbers, z and w, and we want to find the product and the quotient of these 2 complex numbers. They're already in polar form, so I just have to apply those 2 equations from our theorem. We multiply the 2 radii, we get 4. I'm going to add these 2 angles, pi over 8 and pi over 10. I need to get a common denominator to do that. So 5 pi over 40 and 4 pi over 40. I'm going to add them together, you get 9 pi over 40. Same angle right here in the sine. To find the quotient, take 2 divided by 2 is 1, so you don't even bother with the 1, don't bother with the parentheses. Pi over 8 minus pi over 10, so that's going to be 5 pi over 40 minus 4 pi over 40, gives me the pi over 40 right here. and then the sine operates on the exact same angle. Okay, that's it. So now it's time for you to try some of this stuff on your own. I'll see you in class, and I'll see you online.